Okay, we're looking at convex and concave lens diagrams. They're also referred to as converging and diverging lenses. So let's first differentiate between the two. A convex lens is a converging lens, so it looks like this, where it's fatter in the middle and skinnier on the outside. So if we just take a neutral axis here, symmetrical axis, as parallel light rays come in here, let's put a neutral axis in here. Here's our axis. As light rays enter in this way, they will tend to go through a focus point, just like a magnifying glass, where you can tend to take this right up through there, and this goes to our focal point. So all the parallel rays come in and go to that focus. A diverging lens, or a double concave lens, and we're going to stick with symmetrical lenses, we won't get into the fancy ones, but a diverging lens looks something like that, where it's skinny in the middle and fat on the outside. Here's our axis. And parallel incoming light rays then would hit, refract, and again, for simplicity, we're just going to take it once it hits the middle of that axis. It's going to then start spreading out as if the light came from the focus. So it spreads out like that. So again, hits, spreads out as if it came from the focus, and spreads out. So where do we use these kinds of lenses? Well, one common place is with eye disorders. So here normally we have a converging lens on our eye, and as parallel light comes in, say two parallel light rays coming into our eye, they typically focus right on the back of our eye and form an image. But if we're nearsighted, that doesn't happen like that. If we're nearsighted, the parallel light rays come into our eye, but they would tend to focus before the back of our eye, and the image becomes blurry. So you end up with really this little fuzzy image back here, much like you saw in our lab exercise. So on something like this, we need to spread the light out a little bit more, so we would put a diverging lens on, or a double concave, and they have different shaped lenses to do different things. But then we would have our parallel light rays coming in, spreading a little bit as they came in, and then as they entered our eye, they would then refocus, but they'd refocus back to where they were supposed to on the back of our eye. Similarly, if we are farsighted, we'll have these parallel light rays coming in. Farsighted, we can see far but not near. The light rays focus too far back. Okay, so this is farsighted. This would be nearsighted. So then we need to make the light converge a little bit sooner before it gets to our eye. So we would put a converging lens on, which is double convex. So then when we have that light ray coming in, the light ray coming in, it starts to focus before, comes in, starts to focus before, so now it focuses where it's supposed to. So let's take a look at creating some ray diagrams. These are just two examples of how we often use them. So as an example, let's take and now see where the images are formed. So drawing a ray diagram. So if we have an image, let's say back here, and this lens is fatter in the middle, so it is a converging lens. Let's put that up here. This is converging. So again, just like we did with mirrors, we take a ray that is parallel to our axis, and it'll refract as it goes through the light. For simplicity, we draw that neutral axis. Once it gets through here, parallel rays then would go through the focal point. A light ray that would go through the focal point would refract as it goes through the lens, and then come out parallel to the axis. And then our image would then form where those two rays cross. Light came off the tip of the arrow, that's where the tip of the arrow is. Again, light rays going right through there along that neutral axis, goes straight through. You can check by taking a look at putting a line that goes through the center, and it would also travel right through. And they should all converge in the same point. Again, you only need 2 of the 3 lines to figure out where the image is formed. So that's where, for an image that's outside the distant, something greater than the center of curvature, let's take a look at one that's at a different place. Let's say we had an image right at the center of curvature. Let's see what happens here. So here again, you take a light ray that's parallel and goes through the focus, and a light that goes through the focus runs parallel. And you notice that when it's right at the center of curvature, the image is formed right there at the same point. And we could describe that image, which we should have done the other one too, but let's describe this one now. So this one is inverted. It's same size. And it is real. If you put a card here, it would actually form. So anytime you have an image forming on the opposite sides of a lens, it is real. If it's on the same side as the object on a lens, it's virtual. Okay, so this is diverging. And it's a double concave lens. So if we put an object out here, and we take, again, a light ray that is parallel to the axis, when it hits there, it will bend and take off as if it came from the focal point. A light ray that goes through the focal point will then bend and go parallel. Again, these 2 lines won't cross. No image is formed. If it could form, it would be back here where the refracted rays meet, and your image would be here. You can see that this image would be virtual, inverted, and just a little bit smaller.